to make sure everyone can see the slides and hear me. Also, thanks for including us on this great program. Been a lot of great papers. I'm excited to share this joint work with Buzz Brock and Lars Hansen. So let me just jump right in. So there's been a lot of calls for policy implementation to address climate change, and these are based on our confidence and our knowledge and confidence in the climate economy dynamics. However, our view is that the knowledge base remains incomplete to support the sort of standard type of quantitative modeling in the realm of climate change and elsewhere to do this. We believe that to truly engage in evidence-based policy requires that we're clear about a few things. One, the quality of the evidence being used in policymaking decisions, as well as the sensitivity of the modeling inputs based on these evidence that we have. And so our aim is to explore ways to incorporate this uncertainty that exists in climate change models into quantitative policy analysis guided by the tools of dynamic decision theory. Now, this paper is going to take inventory of the consequences of 3 alternative sources of uncertainty, and we're going to provide a novel way to assess them. So these 3 sources come in the form of carbon dynamics, which map emissions into carbon in the atmosphere, temperature dynamics, which then translate that carbon in the atmosphere into temperature changes, and then economic damage functions that depict the fraction of productive capacity that's reduced by temperature changes. Now, rather than using highly complex climate models directly, which would in some sense be quite intractable, we're going to rely on outcomes of pulse experiments applied to these models, which give us some nice approximations to help us pin down climate dynamics we can work with. And then for the damage functions, we're going to follow sort of the ad hoc static damage functions that have been used in much of the previous literature. But importantly, we're going to explore consequences related to the changing of their curvature, which is going to open the door again to another form of uncertainty that we're going to be thinking about. Now, we're going to use a pretty standard policy measure called the social cost of carbon, which is a dollar valuation of an additional ton of carbon in the atmosphere as our barometer for thinking about the consequences of uncertain climate policy. Now, in this setting with uncertainty, we're going to depict this as an asset price where we can use asset pricing theory and tool to think about these components. The social cash flow that we're going to be interested in is an impulse response from a marginal increase in emissions to a marginal impact on damages that'll be induced by future climate change. And this cash flow is going to be discounted stochastically in ways that account for a broader perspective and uncertainty, again, following sort of the tools and frameworks that we have in asset pricing. Now, a common discussion that comes up in environmental economics can often be what rate should we be using to discount these future social costs. We actually find that this isn't necessarily the right question to think about in our framework, because we're going to instead represent broadly based uncertainty adjustments as a change in probability over future outcomes for the macroeconomy. Now, before I get into the model, I want to just note that we're going to be using a particularly sort of simple and intentionally simple for pedagogical purposes model that's going to allow us to highlight some of the key components and features about the uncertainty analysis. Now, that's obviously going to shut down the door to some of the key policy elements that might exist economically, but at the end, I'll touch on some of those. So let me just get through this very simple model and some of the key outcomes we have here, and then I'll touch a little bit more about how we can expand this and how our framework is well built to explore that going forward. Now, as I mentioned, we're going to use some pulse experiments from the climate sciences literature to produce our climate dynamics. All right, and beyond just building a single model, we're going to build sets of models for our uncertainty analysis. So 2 different papers here are papers by Jose and co-authors and Joffrey and co-authors who provide carbon dynamics and temperature dynamics variation and uncertainty. On the carbon side, that's done through responses of atmospheric carbon concentration to emissions pulses going through different Earth system models. And on the temperature side, that's being done using approximations of the dynamics relating the log of atmospheric carbon to future temperatures, which builds on some of this really nice work by Arrhenius that's helped us understand climate change for quite some time. What this is going to do is going to give us essentially 9 different atmospheric carbon responses, as well as 16 different temperature dynamic approximations. And so within that, we have this combination of about 144 climate models that we can look at to think about uncertainty. To help you see what those are going to look like, here we have the outcomes of these pulse experiments where we're taking the pulses through the carbon dynamics and putting these through temperature equations. Now, the top figure is going to show the spread and the temperature responses across 100 years for all 144 models. where on the y-axis we're showing the degrees Celsius temperature change from this 100 gigaton pulse. The bottom left is going to just focus on the carbon component. So we're going to take the 9 carbon components, run them through the 16 temperature models and then average across temperature models to just focus on the carbon component. And the right side is the counterpart for temperature. There's a couple of interesting and important things I want to note here. One, we actually get this fairly quick and flat trajectory that pans out over 100 years, and that's actually going to help inform us about the type of climate dynamics we'll use in our model. Also importantly is that we have this pretty decent spread in terms of the implications of a common pulse. So the red shaded areas on each of these figures is the envelope of all outcomes. The red line, the blue line, and green line are the percentiles. And you can see that across all the models, the impact from a given pulse can range between 1 degree and almost 3 degrees Celsius. And on the carbon side and temperature side, we see importantly related to the types of uncertainty we're thinking about, variation where the temperature impact appears to have a larger effect than the carbon model variation would. So that's going to motivate us to use a very simple approximation, an affine approximation for our climate model, where we look at changes in temperature or the temperature anomaly above the pre-industrial level as this approximation where we take a climate sensitivity parameter based on these pulse outcomes, and it's going to scale cumulative carbon emissions. Now here, looking at those pulse experiments, we're going to take an exponentially weighted average of those, and we produce a climate sensitivity parameter for each of the 144 models. This plot shows the histogram of those outcomes, which again highlights the uncertainty and spread that's there. The way that we're going to deal with this in our analysis is use this type of a model, but we're going to have, in this sense, 144 models or 144 climate sensitivity parameters, and we're going to put prior probability weights across these models. And more than that, we're going to extend it to thinking about uncertainty in terms of structured uncertainty and misspecification that could exist here. Now, the second key component of our model and the third uncertainty component that we're going to be thinking about relates to these economic damage functions that I mentioned previously. Here, we're showing the 3 damage functions that we're going to use in our analysis. We aren't necessarily tied to these as being the true damage functions that exist, but they're going to be very useful for illustrating our purposes of the impact of uncertainty. So the y-axis shows a proportional reduction in economic welfare from damages. The x-axis is the temperature anomaly or the temperature in degrees Celsius above the pre-industrial level. We have 3 functions here that are going to be basically equivalent up until we reach this solid black vertical line, which we're calling a carbon budget, that a lot of climate scientists and economists are concerned things might become more severe after this point at 2 degrees above the pre-industrial temperature level. Now from there, we have 3 climate damage functions. We have a low damages, which after about 5 degrees Celsius increase leads to about a 5% reduction in output. A high damage function, which leads to about a 20% reduction in output after a 5 degree increase in temperature. And then we have this extreme damage, which just highlights, in some sense, a smoother carbon budget that potentially there could be very negative outcomes after we reach a 2 degree temperature threshold. Now, I want to talk a little bit about the details of this figure, and this will be one of the few equations I actually show you because it's going to introduce one of the important components of our analysis. So we're going to use this piecewise log quadratic damage function, where temperature anomaly y, this function gamma of the temperature anomaly, is a log damages given by this expression, okay? The gamma 1 and gamma 2 are common across those 3 damage functions I showed you previously, but there's going to be uncertainty coming in the form of a jump process with m absorbing states, and those absorbing states are going to correspond to different values of gamma 3m. So after this threshold gamma bar, or sorry, y bar, this additional quadratic piece turns on, determining the curvature of the damage function. Now, prior to this jump taking place, the decision maker, the planner, doesn't know which is going to be the actual damage function. And so we're going to place, much like we had in our histogram, we're going to have a prior probability specified on each of these gamma 3m's. And then we're going to have this jump process that's going to occur very close to the threshold, and we'll specify an intensity function that's going to be localized right around that y bar, that 2 degrees threshold that we mentioned. Now, I want to highlight this key point. The information dynamics here we think are particularly interesting, and in contrast to much of the previous research being done, including our own, where the analysis is either static or the uncertainty is never actually revealed. There's this really neat structure in terms of when this is going to be revealed and how the planner responds to that and the uncertainty that's involved with that that's going to be an important component of our analysis. So again, I'm going to jump right in now to the uncertainty analysis. Just as a reminder, I'm going to keep this at a high level, and essentially you can think about the damage function and those climate dynamics as the key components we're thinking about in the model. The remainder of the model, which is going to be a single capital stock and other important components, are going to be largely separable. Again, that's sort of imposed by us to keep this pedagogically simple and informative, but we're going to be able to use this same uncertainty structure and analysis on these nice, simple social planner problems where we get a simple policy structure to think about the impacts and the quantitative adjustments. This same structure can be applied into more rigorous settings as well. So in terms of the uncertainty adjustments and the uncertainty analysis we're interested in, we're going to try and open the door here to a comprehensive assessment of uncertainty based on broader notions of uncertainty. We're going to use recent formalisms from decision theory under uncertainty to think about how this matters. And we're going to include multiple types of uncertainty. You could think about ambiguity, which is going to be uncertainty across models. This would be sort of a very structured way of putting probability weights on those climate dynamic models or the damage functions, and thinking about how those might be sort of weighted in different ways if we're concerned about uncertainty, as well as potential misspecification, either about the damage functions or the climate dynamics. And so we're going to use decision theory as a way to form uncertainty quantifications, thinking about how those lead to adjustments in the social cost of carbon set by the social planner. And that's going to inform us of how much this might matter. So let me give you a little bit of the details of how we're going to think about this uncertainty. We're going to think about we're going to examine altered probabilities that are going to be implied by 3 different cases, and we're going to combine some of these. Misspecification about the local climate dynamics, misspecification about the damage functions, and then ambiguity over structured uncertainty across those climate dynamics as well. Now, the way we're going to do this is following the previous literature and opening up some new ways to think about it, where we're going to have a minimization problem where the planner actually internalizes this sensitivity analysis, makes optimal endogenous choices about how much this uncertainty might matter. And that's going to introduce these parameters, CB, which will be related to the misspecifying of local dynamics, CP, which is going to be related to the misspecifying of the damage function, and CA, which is going to be related to the ambiguity. Those are going to guide our sensitivity analysis. Now, those are going to be, from the decision theoretic perspective, preference parameters that govern aversion to uncertainty, broadly conceived, in conjunction with this endogenous minimization problem that the planner is using and the current states of the world that they're in to determine how much this matters. Now, that's a key part, is that the altered probabilities that we're going to be looking at are not intended to be the beliefs of the planner. Rather, they're reflecting how large their concerns about uncertainty are, and then helping them adjust their policy in conjunction with that. Let me visually talk you through this uncertainty to show how this might matter. So here we have a figure of the value function, and this is going to have temperature anomaly on the y-axis. We have at the 2-degree threshold, we have this dashed black line. So on the left-hand side of that, we have a solid blue line, which is the value function or the welfare, the continuation value for our social planner here. On the right-hand side of that line, we have a dashed line, which is the certainty equivalent for the value function, essentially what the planner expects to happen after this jump where the curvature is revealed. And then the 3 colored lines are the damage function conditional on a specific, the value functions conditional on a specific damage function. Now you can see that as temperature anomaly increases, the value function decreases, the externality impact and damages become larger. That makes sense. And what the role of uncertainty is going to do is the following. The ambiguity or misspecification about climate dynamics is essentially going to shift where these solid lines are showing up. It's going to tilt and distort them in certain ways. And then this concern about uncertainty related to the damage function is going to alter and distort where the solid blue line and the certainty equivalent after the jump are meeting up. So here in this specific case, uncertainty for this specific example where we put equal weights on the different damage functions is leading the planner to have this certainty equivalent expectation that's going to be below the high damage function result, not yet at the extreme damage function result, which is again is highlighting these are endogenous determinations that aren't simply pushing all the weight towards worst case outcomes. but sort of optimally taking into account what do we think matters. So given that, I'm going to jump into a couple of the key results, looking at first the emissions trajectory and then the social cost of carbons under different uncertainty penalization configurations, okay? So these are going to be simulation results. We'll go for about 90 years, and these are in gigatons of carbon, our emissions pathways. That top line is what we'll call the baseline setting, where there's no concerns about uncertainty. Here we start with emissions that are on the order of 9 gigatons of carbon, and those are decreasing over time because of the increasing impact of climate damages. Now, as we start to turn on components of uncertainty, moving from the red line to the yellow to the green, and the green to the blue, as uncertainty becomes more severe, we see interesting dynamic effects. First, an initial decrease in the emissions that can be quite substantial when we get to these larger uncertainty components that can change over time. In some cases, these difference in emissions will persist, and sometimes they will close together. And this is just one side of the coin, so let me move to that barometer that I mentioned previously, which is the social cost of carbon. Now we saw here, I'm showing you the social cost of carbon trajectories from the simulations, and I'm doing them in logs. We're scaling these all by the initial sort of marginal utility of consumption so that we take out any of the sort of growth effects and we focus mostly on climate and uncertainty effects. And again, where we saw the highest emissions, that's being reflected by the lowest social cost of carbons that are imposed by the planner's policy choices. And again, as we increase uncertainty, we see an amplified social cost of carbon that can be on the order of increasing that social cost of carbon by 30% or more. Now, the question is, we've introduced some free parameters. Does this really make sense? Are we sort of going beyond the mark? Are we just throwing in uncertainty to sort of get to the most extreme cases? And so the way that we're going to look at that is by looking at how these distorted probabilities are shaping up in these different cases. And I'm going to focus on distorted probabilities related to this yellow case, okay? The first set of distorted probabilities I'm going to show are the uncertainty adjusted damage function probabilities. Now again, remember in this case, we put equal weights on the extreme, high, and low damage functions. And the planner endogenously distorts these probabilities as a function of temperature so that even at the no initial temperature anomaly, we see that they've increased the weight on the extreme damage function to be up to almost 40% now. And then as temperature increases, we see a shift away from probability on the high and low damage. And as we draw near to that threshold where the curvature of the damage function is going to be revealed, we see an increase up to about almost 60%. Now, we think this is informative, one, because it shows that there are important dynamic effects, but two, that these probabilities, we don't view these as being overly ambitious, or we're not loading full probabilities on the very worst case outcomes. If you look at the counterpart for the uncertainty adjusted climate model probabilities, again, this is that original red histogram I showed you on the climate sensitivities. That's the red histogram here. And the blue shows the distorted histogram based on adjusted probabilities for uncertainty. Again, we see a shift from the lower outcomes in the left tail to the more severe outcomes in the right tail. But again, where we saw these reasonably significant impacts on the social cost of carbon, we don't think that the uncertainty adjustments here are too large. We think these are fairly reasonable and informative adjustments to think about our analysis. So I've got about 1 or 2 more minutes, I think. So let me discuss briefly 2 key components. The first one is going to be what we think is a pretty novel and interesting contribution is an uncertainty decomposition. So basically, because we're using, in some cases, misspecification, and in some cases, the smooth ambiguity approach that's more structured, we're going to exploit that, which allows us to open the hood on this uncertainty. And we're going to do that by doing a decomposition of the 3 uncertainty components in our analysis: the carbon dynamics, temperature dynamics, and economic damage functions. The way that we do that is by asking how an ambiguity-averse planner would adjust their policy when they're constrained to just look at specific components of the uncertainty. And so we're going to look at first each individual component, then we'll look at pairwise components of uncertainty. And for comparability, we're going to hold fixed the emissions trajectory, and they're going to be held fixed at the social planner's optimal emissions when they're considering all the uncertainty components, which is important. It could be very different for different trajectories.
Michael, 1 minute warning.
Okay, cool. So looking at these individual components, you can see that there are very different impacts across the different components. So carbon and temperature have both And here I'm showing you for the simulation trajectories, the log differences. So this is essentially the contribution to the social cost of carbon and a percentage coming from uncertainty, okay? So for the total, the red line where all the components are included, this is anywhere from 20 to 40% of the social cost of carbon. Now, carbon and temperature are flat and lower, and that's because of the emissions trajectory here. And we see that damage leads to a large impact that's dynamically increasing. When we move to the pairwise contributions in this uncertainty decomposition, we see importantly that it's the interactions of damage with temperature, damage with carbon that really matter. And we have these nice multiplicative effects that we can identify because we can decompose this uncertainty decomposition. So in the last 30 seconds I have, I just want to highlight again this point that we are working and have computations in progress on some richer economic settings. These, again, our setting is focused on this sort of nice pedagogical setting, but our framework is very nicely set up to explore additional policy settings, more complex economic settings, and in particular, we're looking at two capital models with some key coupled dynamics. One of them is a coal versus oil production technology where we have two fossil fuels that are both attractive for production, but one of them produces more emissions, which allows us to then open the hood to thinking about uncertainty in policy pertaining to differential energy inputs and how to deal with those. Another is looking at clean versus dirty, where we have a dirty technology that's more productive, but a planner can invest in R&D, so we can think about uncertainty about how that R&D to improve the green sector might matter, how uncertainty about the policy and dynamics would interact with that. And then finally, looking at the case of climate vulnerable versus climate resilient technologies, where again, climate vulnerable faces additional damages, which opens additional uncertainty, and we can think about policy for monitoring and limiting this. I'll just give, yeah, here's my conclusions all in there.
Oh, all right, good. Thank you very, very much for a very clear presentation. Our first discussant is Mara Gwant. Mar, are you on mute, Mar? No.
Yeah, I was all fired up already going. So yeah, so thank you so much for the opportunity. So as you may know, I'm not a macroeconomist. I'm an industrial organization economist working on energy and environmental topics. I usually work modeling very specifically given industries, so the electricity sector, the cement industry, or some other industry. Recently, I've been working on a commission commissioned by Olivier Blanchard and Jean Tirole, and together with Christian Gollier, thinking about the challenges of climate change advising President Macron. And that has given me a bit of a more macro perspective. And honestly, it's quite scary and frightening as you go into the macro perspective for someone who has been focused mostly on how to make cap and trade work in the electricity sector or in manufacturing. So in today's presentation, I will honestly be quite critical of the work. I'm a pretty reasonable person, so I don't want you to take this as confrontational for the sake of it. I will be quite critical with the work because I deeply care about such a grave matter. And I think you might not be getting quite the right answer. So I'll offer my comments and I hope that will help revise the model. So I think Michael was very clear in presenting the paper. This paper is about how to do predictions from a macroeconomic model that take into account various sorts of uncertainty. I'm not an expert in continuous time macroeconomic modeling, but it seems to me that the approach has many interesting features that get combined, such as model misspecification, Brownian jumps, and all these different ingredients that Michael was explaining. So an insight that I thought was interesting, again, not being familiar with the literature, is that they present these representations of uncertainty and probabilities that take into account the ambiguity version and how other misspecifications factor into the model. But in some ways, for someone who's not familiar with how the under the hood works, I can actually look at these probabilities and make an assessment of what they are thinking about. So as you can see here, let me put, here on the left, I have the climate sensitivity, and they are telling me the red distribution is the true distribution. Someone who's more ambiguity averse will respond more as if the blue distribution were the true one, understanding that it is not. Similarly here, we have these probabilities. They should be weighted 1/3 each, but someone who's more ambiguity averse, someone who takes into account all these different processes that they put into the continuous time model should actually end up placing more weight on the extreme damages. So the bottom line, and this is where I will be most critical, I think, honestly, the mathematical model seems interesting, but when we get to the quantitative implications of the model, the paper will claim that adding these effects makes the planner more conservative. But I guess what I will argue in my discussion is that the planner is not being conservative at all in their implications. So a brief summary of the model, I will go over different details that Michael emphasized. So the model is very simple. I know Michael called it pedagogical, but again, if we care about the quantitative answer, we cannot just stop at the pedagogical model. It's an AK model with emissions as a Cobb-Douglas that incorporates economic damages in an interesting way. Actually, economic damages are introduced via N. So think about consumption and investment equal to alpha K, and then the utility being this Cobb-Douglas function between effective consumption and emissions. And here the key is that effective consumption is deteriorated as emissions accumulate into the atmosphere via the increase in temperatures. So the more emissions are accumulated into the atmosphere, NT keeps growing, and effective consumption holding the uncorrected consumption constant, effective consumption keeps decreasing. So the meat in the model is how to model the uncertainty surrounding these relationships that put the economic damages into play. So how emissions will turn into temperature increases, and how then these temperature increases will hinder our ability to thrive. And to inform those models these objects, these stochastic objects, they will use scientific evidence as well as some off-the-shelf economic scenarios, as Michael was explaining. So these are the two key ingredients. One is the climate sensitivity one that I already showed you. And the other one is these three cases, the Nordhaus case, an intermediate case, and extreme case. So I plotted here over a bit of a longer range so that you can see what these scenarios are telling us. The extreme case, it's telling us that at 6 degrees Celsius, we will all die. The intermediate case is kind of a bit in between, but it significantly reduces welfare, holding everything else constant. This is the N, I guess. Or the effective 1/n kind of reduction. And the Nordhaus one, you can see that, we can heat the planet by 10 degrees Celsius and only suffer 20% in welfare. So this is honestly, does not look very realistic if you are now on top gonna add R&D. So this Nordhaus case is extremely optimistic, and it can only be explained with R&D already baked in it. So I would be quite cautious in how you think about R&D, given that these are the scenarios that you're considering, because these scenarios in some sense are already heavily relying on significant R&D, I would say. So this is just a small caveat. So let me now substantiate my claimed criticisms that so far I haven't made explicit. So a first criticism is just on the pure calibration of the model. So the model starts concentrations at 390 ppm. This is something you probably have seen on the news. Actually, this week we've seen it on the news a lot, because we have discovered or confirmed that we are now already at 415. So for those of you who do not study climate change, these numbers might not mean much, but going over 400 is already something that had been frightening scientists for a really long time. And 415, it's already a lot of the cake that's built into the model that we are dealing with here. I want to show you the exponential perspective now that we are used with exponential trends. So this model starts here, and it's not too far off, it's 2010, but in 10 years you can see how parts per million have kept increasing at an extremely rapid rate. So even just these 10 years are assuming, basically we are giving ourselves 10 years that we just do not have. And this is easy to fix. So that's at least an easy one that you can handle. So the second criticism on how the scientific facts are incorporated in the model, and to be fair, this might be my lack of understanding of how the stochasticity is modeled in the paper. So it's very unclear to me from the writing that I found a bit dense, how the noise in the scientific evidence is incorporated into the Brownian motion. So if I understand correctly, the thought experiment behind this scientific evidence, so this is the scientific evidence, as humans, we are drawing one draw from this scientific evidence. There are 144 models, one of them is right. We just don't know which one it is. And this is the noise that we get from these different 144 models. So my worry is that this is not what the authors are modeling. My worry is that the authors are modeling something that looks more like we are drawing from this distribution repeatedly. If we are not drawing from this distribution repeatedly, we need to incorporate learning into the behavior of the planner. But at least from my reading, it seemed like the probabilities of these different 144 models were not indexed by T. So if the planner is not learning, we are ignoring optimal behavior in tail events. So we are ignoring the fact that we might be here repeatedly. Indeed, I feel like from the model, again, and this might be my lack of understanding, it's almost as if the planner were behaving as basically responding to the mean drift of this distribution. So in spite of having this distribution of uncertainty, because either we assume that we keep drawing from it, or the social planner behaves as if we keep drawing from it, I feel it's only responding again, almost or kind of, to the mean drift and ignoring this tail behavior that in the literature has been so greatly emphasized. So let me now turn into the economic specification of the model. So I understand this is a simple model, but it just cannot be a model for us to make recommendations on how to deal with climate change. So in this model, emissions appear in the Cobb-Douglas with an index of, this is ADA in their paper, of 3.2%. So it implies we can cut our emissions by half instantly by just reducing our utility by 2.2%. It also implies that we can cut our emissions by 99% by just reducing our utility instantly by 13%. And it implies that we can cut our emissions by 99.9%. We can virtually decarbonize our economy immediately by only spending 20% of our utility. Honestly, this sounds great, and I wish we did live in that world, but we do not live in this world. So I am a bit concerned about the predictions on the model, because in this model, it's almost as if there is no climate change problem. So we can see the issue of the dynamics here. We can see that at 0, depending on the ambiguity version of the planner, we can decide whether to be at 8 or we can decide whether to be at 5. Again, the presence of sunk capital in the fossil fuel industry, both from a practical perspective, but definitely from a political economy perspective, creates huge challenges to making the needed progress. And this sunk capital will not go away. I am encouraged that you are working on extensions, but honestly, I would suggest that you don't spend any time on your first extension. We don't live in a world where we can afford to move from coal to go to the oil industry. It's not the world we live in. So finally, on the policy uncertainty in the model, this is not covered, but I also think it can lead to misleading recommendations. So in this model, a social planner can choose how we can reduce emissions in the planet. And again, I wish this were true, but it's not just what we are facing. There's a huge tragedy of the commons. Every year we say next year we should reduce our emissions. And as you could see from the graph I showed you, we are on an exponential growth in emissions. So this seems extremely relevant, even within the pedagogical framework, to incorporate into the model. You should have some latent emissions that the planner cannot control and that can go really wrong in the model. Here I wanted to put a bit of a kind of side note that's got me thinking lately. So as economists, we tend to dismiss these kind of cliff ideas, 2 degrees Celsius, something we really need to avoid. 0 carbon by year 2050. No injection combustion engines by year, whatever. And yes, as an economist, I agree that having this kind of very fixed targets might seem wrong, but we have to recognize that it's one of the few things that has gotten some international reciprocity. Whether countries pretend to stick to these commitments, it's very unclear, but at least it's gotten them to speak up and promise things that probably won't be delivered. So, in spite of all this optimism that's built into the model, this is a doomsday model of climate change. So in this model, there is no room to fight climate change other than substitution and degrowth. So this is a model about how we eat the crumbles of what's left, where we are overstating quite a bit the crumbles that are left. So the discount factor in some sense matters a lot because it's a pure cake eating problem. Without emissions in the model, welfare goes to 0 as temperature keeps rising until we all die. So this unavoidable fate in the model is only disguised by the fact that there are some unrealistic economic assumptions. And the last point I wanted to make is that there are also possibly implausible carbon budgets. This is related to my first point that I told you that the model is starting in 2010, but we have already burned 10 of those years. It could also be related to the model of uncertainty that I mentioned on the climate sensitivities. Bottom line, however, the model claims that we can stick below 2 degrees Celsius, which agrees with what scientists are recommending left and right, by only cutting our emissions in half. So these are some simulations that are in a great website, honestly, for divulgation, Our World in Data. And they show what different climate models are telling us our carbon budget is left. So the carbon budget is the area below our emissions. And what these models are telling us, the scientific models from which we supposedly derived these emissions paths, it's really this area under here. So I am worried again that there is a mismatch between the scientific evidence that's used and the given state of the art of the scientific evidence. So again, maybe the 4 or 15 parts per million will fix some of these recommendations, but in the model, they will still look, whatever alternative you derive from the model, it will look extremely cheap, it seems to me. So I wanted to finish by just saying that climate change is the biggest threat that humanity has faced. And if you look at the numbers long enough, and that might be 2 minutes, you will convince yourself that that's the case. So our duty is, if we want to inform the debate, is to take the scientific and engineering facts accurately. So I like this paper because it does try to put the scientific facts carefully in the model, but I feel it's really not accurate enough when it comes to the quantitative conclusion. It also misses the state of the art in, as of now, our inability to abate carbon, although maybe some extensions with R&D will help in this criticism. So my suggestions for an improved paper is to really try to reconcile the results with the current scientific evidence and to try to consider the role of emissions-intensive capital, which it sounds like we are already doing. It was not in the version of the paper that I reviewed. So as a final kind of a slide, I have a how can economists help? And I know number one will go very bad in a room full of macroeconomists. But in my opinion, I think we as macroeconomists, as economists, we should really stop quibbling about what the optimal path of emission reduction should be. I complained about your path of having emissions, like reducing emissions by half. That said, I would be glad if we could achieve a reduction of emissions in half. I really would. I feel no matter what recommendations we make, we will fall quite short. So I think we should in some ways try to stop arguing about what the optimal path will be, because we might well be at a corner solution. No matter what optimal path we derive, we will probably fall short, unfortunately. So I think we need to spend a lot of time trying to think, okay, how do we get closer to even the most optimistic optimal path that we can derive by thinking creatively on how to decarbonize our economies and how to phase out fossil fuels. Again, natural gas or oil is really not a solution here. Finally, and unfortunately, I think we need to creatively think on how to preserve lives in the presence of already happening very extreme adverse events and only bound to increase. So thank you so much for giving me the opportunity to discuss the paper, and I look forward to the discussion.
Thank you very much, Mar, for a thought-provoking discussion. Our next discussant will be Per Krusell.
You see this okay?
Yeah, just great. I mean, you could put full view on it.
Yeah, I'm going to. Yep. I just had to unmute, so it took a second.
Sure.
Yeah, thanks. It's been very interesting to read and think about this work, and kind of maybe luckily I have a bunch of comments, but they don't overlap so much with Mar's discussion, which I found super interesting. I want to think about more. So you get a different set of comments here from me. So I guess the issues are these big ones: significant climate change, large uncertainty, extreme damages thresholds, very scary stuff. And I agree with Mar's assessment, and clearly a reason for precaution in policymaking. So that's kind of what motivates this approach. It's like a structured way to do policy under this uncertainty. But the focus is methodological somehow. I view this as maybe proof of concept, or and this is also reflected in Mar's comments, but I'm not going to develop them so much. But basically, the authors use developments in dynamic decision theory to analyze ambiguity and model misspecification, and then show how these features guide social planner decisions. And let me just emphasize, this is kind of, they look at really planning problems with uncertainty. It's not decentralized models where you can identify households and firms. It's really a planner running the show, and but taking into account, maybe benevolent planner, taking into account that we don't know a lot of things. So basically, they say in the abstract, their approach reduces the many facets of uncertainty into a low-dimensional characterization that depends on the uncertainty aversion of a decision maker or fictitious social planner. And I think the focus is more on the stochastics in each model and across models than on the economics. So in that sense, kind of this is in line with what Mar said, but so uncertainty in climate science. Now I've reproduced the graphs here, and you have to remember what's on the axis. But so the first paper was by Joes et al. 2013, which is the carbon cycle set of experiments, and you see years here up to 100 years, and the temperature change from 0 to 2.5, and then back down a little bit. The idea here is in these papers, they emit all at once in the beginning of time 100 gigaton of carbon, which is like 10 times what we emit in a year, roughly. So it's like a decade boom out there, and then you let it sit, and you see that the response of temperature is this. It kind of interestingly, within 20 years or within 10 years, the temperature is kind of stabilized in this ensemble of nine models. Okay, so temperature dynamics are pretty fast. I mean, climate change is a long-run thing, but you see temperature dynamics are relatively quick. The climate system taken by itself, so the running various, in this case, 16 models by Joffrey et al. Did that, and you see bigger ensemble. So this is what climate scientists and carbon cyclists do, they have a bunch of models. Mars said one is the right one. This is what economists tend to think, one is the right one. It's kind of the way we think. They don't exactly think that way. There's just a bunch of models out there. Even the same model, they simulate for different initial seeds and you get different outcomes. Why? Because they're chaotic systems and so on. Climate models are very complex. But anyway, they give you a bunch of output, and if you put them all together, 144 models. I did some factorization here because I can't do 9 times 16, but I'm convinced that it is 144 now. So I did check the reference. I talked to my local go-to natural scientist here, and he knew these papers very well. He said this is very solid work. So, and I mean here, I'm not the expert, but the expert I talked to said that this is very kind of updated and good stuff. So we can take this to be. But of course, remember what is kind of interesting is this is just one pulse of this amount. So for example, do we see tipping points in the climate system? Do we see tipping points in the carbon cycle? Well, in a way, we can't really tell from this set of graphs. Why? Because, well, there's always this one pulse. I mean, suppose you did twice the pulse, would the system then kind of just explode? It's not clear. So I think these experiments don't speak to the non-linearities that are potentially in the tipping points that might be in the carbon cycle and the climate system. What I should add to that is that what they then do actually is not use these models. They summarize the results in these models and map them into that temperature graph that you saw, or our climate sensitivity graph, the bar chart, which is really a recent result in climate science, which is that you can approximate the temperature outcome just by saying it's proportional to the cumulative past emissions, like a remarkable stylized, simplified model. The temperature increase over pre-industrial is proportional to the cumulative past emissions. And you don't have to think about the carbon cycle, just how much you emitted. This is a relatively recent result by Matthews. Now, of course, we don't stop there because that proportionality coefficient, it's there in all the models, it's there in all the simulations, but then the models vary. So we don't know what so there's a variety of possible values for that proportionality constant. But actually, the Matthew result somehow directly says that the summary of the carbon cycle and climate system stuff is that they don't see big tipping points, at least not kind of visibly in that line of work. It's really remarkable that it's so linear. And this was a bit of a shock to me, but I don't know, that's the models they run. Then there's the other element that Michael described well, the damages. And the source of these, as you said, it's kind of like a working example. I mean, I would say it's essentially made up. I mean, that's not meant to be criticism. It's just would be nice to refer to studies, but here is where empirically oriented economists must kind of gather more and more evidence to help us see what's going on. I mean, issues are, what are the sources of the nonlinearity in damages? If you think about it, damages. What's the nonlinearity? A nonlinearity may be that you flood Bangladesh. So I mean, but it's when you start thinking about nonlinearities in damages, it's not obvious to me. I mean, it is that when you pass a certain threshold in temperature, humans can't survive and so on. There are a few of those. So I just think it would be nice to relate to them when you model this. And people will ask, what about adaptation? So why can't people move from the areas that are so warm and so on? I mean, you're just bound to get these questions, and it would be nice if there would be some discussion, because I do think, like Mar said, you need to go more quantitative, especially in the economics part. And this is where, this is the economics. So in a way, I think the climate science stuff here is very solid in a way, but the economics is a bit too made up. But it works well for illustration, of course. So here's my way of describing the model. Is a bit different. So I'm going to describe a static model, which I think this can be viewed as, in a way, so Nordhaus's model kind of looks like this. Think of preferences as log C. Okay, you consume. And then production comes from a Cobb-Douglas production function in capital, labor, and E is energy, and let's say it's fossil energy. And then you have to subtract some resource costs here because it costs something to produce the E. Then the orange thing is an externality of using E. A high E makes D lower. Why? Through the carbon cycle and the climate system, here's the externality, and here's how you can just do a simple static model and derive the optimal Pigou tax. I mean, we can define a competitive equilibrium and without taxes, with taxes, and work with this. So that's kind of the first model. This paper, although, as Mars said, it's an AK style dynamic continuous time model with Brownian motions and so on. Think of it in the static version. I think it looks like this because it looks the same. So it's true that E shows up in utility in their framework, but I can, take log C and, you could think that this E here is just in utility instead. So, I mean, it benefits you in utility. So I would say this is again kind of a case of Pigou, but it's a little bit, maybe this is just a question to the authors. I didn't understand why there was no GOV. So if you do laissez-faire, no tax, wouldn't E be infinity? I mean, I didn't see the exact carbon budget that Mar talked about. I mean, carbon budget can mean different things. Is there like a maximum? What's the cost of extracting more E? I mean, maybe it was there and I just didn't see it. The GOV here. So of course, their planner will never want to use an infinite amount of E. That's what would happen in equilibrium if there is no cost of using it. But anyway, so I would say this is kind of, this model it's macro style and you can think of reasonable values for all the parameters. New here, Mar was talking about 0.03 being low. New here is, in the macro style model, it's the share of energy in costs, in gross output. And that's like 5 to 10% depending on, so it's not 3, but it's not super high either. Now, and this is a static model, but I think of it as a model for like 50-year period or 20-year period at least, but or even 100. And then Cobb-Douglas is not crazy. In the very short run, I think our economists would stop pretty much if you just reduced E by 90%. I mean, it wouldn't share the Cobb-Douglas feature that you see in front of you. In the very short run, I think you think Leontief instead. So the elasticity substitution really should vary with time, and you can substitute, but only if you're given enough time. But anyway, for static model, I think this is reasonable. Okay, so I think this is nice because you can think of adding an ex-ante stage and make a policy choice ex-ante, and then add your uncertainties in the various places. And it's an entirely, much simpler model. I think just would be nice to think about it that way. And it would allow you to connect more with the quantitative studies. The only thing that's missing here is discounting, which of course is important, but you can't capture everything in a simple static model. Okay, but the economics of the static model, this is something that we looked at recently we looked at it in a paper that the authors kindly cite, which is related, as you'll see in a second. But we revisited the issue very recently, just to try to understand the results a bit better. So we really took the simple Nordhaus model that you saw here. And then we asked the following question. We thought about model misspecification too. So we thought of 2 errors you could make. Error 1, what if we choose a carbon tax based on thinking that D of E involves huge externalities? It's really, really bad. And then we quantify this by precisely looking at those curves that the authors look at, by taking the highest curve, the most warming you could ever get, plus taking the most drastic empirical estimates of damages. So suppose you base your policy on that, but actually, and you choose that in the ex-ante period, but actually the externality is close to zero and climate change is no big deal, okay? So we computed that error, I mean, as percent of consumption, and then we did the reverse, error 2. What if we choose not to tax carbon because we think E barely affects D, but in fact, it does in this extreme way, again, with reference to the extreme damage functions and so on. And then we found that the first error is actually not a big deal. It's not a big deal to tax carbon at a relatively high rate, the rate you need, based on thinking that climate change is really dangerous. You will, of course, it will be a drag, but it will not be a huge drag on welfare in this kind of long run perspective. Whereas the second error of not taxing when really you should is actually huge. So there's a built-in asymmetry. And in our current work, we are trying to understand this. And basically, if you go from a zero tax to a very small tax, when you should tax, then like every unit of tax is super helpful in combating climate change, in reducing the externality, because the externality is big. So it really pays off to raise the tax from zero to whatever small number. Whereas the opposite, going from a zero tax to a positive tax, isn't very costly if climate change isn't a threat. Then a zero tax is the right thing to do. But a small departure from that is just like the objective function is pretty flat around zero. So using a positive tax, even a relatively big one, isn't very costly for a utility. So you can actually understand these results based on these asymmetries, based on the simple model. And this is how it plays out kind of if we do the dynamic model over time, where the black is the consumption loss of making the error of thinking climate change is not a big deal. Whereas the red one is the error of acting as if climate change is a big deal, but it turns out not to be. So for us, this type of study indicates that, if I don't know which error I'm going to end up making, and I'll do precautionary and do the red one, and so on. So so now my perspective is to compare this to the present paper. So what I'm not sure in the paper is to what extent the argument the authors have for precautionary behavior, which is kind of coming through ambiguity aversion and distorting the probability somehow to act as if you think it's really bad. Whether the results they get or what part of the results come from this built-in asymmetry that we have documented, and what just comes from that, and what comes from the ambiguity aversion that they assume. So I think it would just be good if they explain that, because it would help me think about these models with ambiguity aversion. More generally, kind of, I would like to anchor things a bit. So I'll be done momentarily. So I would say, as a way of describing what macro people, again, I am a macro person, unlike Mar, working in this area. So here's like what I think macro people working in this area have done. They have thought of ways to make the optimal carbon tax become a big number. I mean, that's just, I think, a description of what they've done. And I think they've done it because, I mean, they're concerned, and some calculations like Nordhaus's gives an optimal tax on carbon that's not very big. And it's like, well, is that wrong? And what's wrong with the model? So we know now that if we use a discount factor as very high, low discount rate, you can get the numbers to go up. If you assume risk and you assume high risk aversion or big tail, fat tails, you can get the number to go up. You assume a high curvature on damages, you get the number to go up. You assume that higher temperature lowers the growth rate instead of a level effect, you get the number to go up. If you assume a major tipping point in the climate system or in damages, you get the number to go up. So for me here, I mean, all of these hypotheses is what they are. They need to be evaluated kind of quantitatively, and you'd like to relate to something. So on this list is also ambiguity aversion. Oh, there's uncertainty, and we're worried about it because we don't quite know what the right probabilities are, what the right model is. So I would like, just like I would like to know, some of these issues are just ethical, like discounting may just be an ethical issue, but some of the other ones are just, we should just be able to learn more and find out. So what should I base my calibration of ambiguity aversion on is my question.
Okay, wait, one more warning.
Yes. So kind of what's the guidance on that would be useful. Final thoughts is that I fully agree, I mean, reflected in my own work, that this uncertainty is super important, should lead us to be very cautious, should drastically lower emissions. My worry a little bit is that we as economists can contribute productively in this area more with economic analysis, explaining costs and benefits, figuring out how to do things in a smart way, explaining costs and benefits of different policy actions, using our understanding of markets, because that's what we are good at. I'm less sure that kind of formalization of uncertainty is the way forward. But that's maybe more on the policy side. I fully agree that it makes sense to think about it the way the authors think about it. But I'm kind of worried that people won't listen to us because we came up with this great way of thinking about uncertainty. Rather, if we can explain this is how we should use markets to move forward, then they might listen or not. But okay, thanks. Sorry.